Hi, I'm Alicia Matson, and I'm presenting the paper PerfFuzz Automatically Generating Pathological Input. This paper proposes a new fuzzing technique focused on performance bugs rather than crashes. The goal is to automatically generate inputs that trigger worst-case algorithmic behavior. Unexpected performance issues can lead to software failures, security vulnerabilities, and DOS attacks. Common performance test inputs include handcrafted tests, standardized benchmarks, typical real-world input, and inputs from users reporting problems. These either test average case behavior, have human bias, or the damage is already done. Worst case behavior remains hidden until production, which is why fuzzing is important, so that this does not happen. So the goal of PerfFuzz is to automatically generate pathological inputs that expose performance bottlenecks without domain knowledge. So it is a feedback-directed mutational fuzzing. Pathological inputs may cause algorithms to run much slower than expected, so finding them early on can prevent major performance failures. So we'll start with what fuzzing is in general. Fuzzing is an automated testing technique that generates many inputs, runs them against a program, and then observes its behavior. So there's many different ways to do this. Feedback-directed fuzzing uses runtime feedback to guide its input generation. And one of the most widely used fuzzers is AFL. Traditional fuzzers prioritize finding crashes or finding new code paths. Next, what is a pathological input? A pathological input is an input that causes worst case algorithmic complexity in a program. So an example of this is triggering an O of n squared behavior in a sorting algorithm, causing repeated hash collisions, or creating deep recursion or really long loops. The key idea is that different inputs stress different components of a program. These inputs might not crash the program necessarily, but they'll make it extremely slow. So now an overview of PerfFuzz. As said before, it uses feedback-directed mutational fuzzing. So it also associates each program location with an input that executed it the most times. It also uses multi-dimensional feedback, where it's maximizing execution counts per program location and finds the distinct performance hotspots. So it targets individual parts of the program to different hotspots. So now we're going to talk about word frequency. This is just a simple word frequency program. So we're going to use this to kind of show what PerfFuzz is doing and different examples of what can happen. So obviously, word frequency counts the frequency of words in an input text. It is implemented using a fixed bucket hash table with the key function of add word, as you can see on the right. The potential performance bottlenecks in this would occur with long words because then the hash computations are a lot lower, and then with many distinct words because that will cause a lot more hash collisions. So this is a simple example of how inputs affect an algorithm's complexity. So now here are some examples of the mutations that could happen. Um, the first one would just be the simple seed input. It's just a basic sentence that shows that the word the is said twice in it. So with the first mutation on the right, it changes the O in fox to an I. This does not increase execution count for anything, not add word or the complexity of the word. So this input would just be discarded. Next on the bottom left, it replaces the I in quick with a space. So this adds an execution for add word, obviously because now there's one more word than before. This is saved. This would be saved since no previous inputs executed the CFG edge that invokes this function 10 or more times. And then with the last one, it replaces the space between brown and fox with an underscore, making it one whole word. So this uses add word one less times since we got rid of a word. But since the brown fox and dog have the same hash value, this would cause a collision resolving in linked list traversal. So this means that this would also be saved. So what are other ways to identify bottlenecks? Normally, developers use tools like gproc, Valgrind, and other statistical debugging tools, but these all require inputs that trigger the problem. You need the specific input. So what do you do if you don't know these inputs? That's where PerfFuzz attempts to obviously automatically discover them. Next, earlier I said that um, in the quick brown fox jumped over the lazy dog, it executed another CFG edge. Now I'm going to explain what that is. So CFG stands for control flow graph. So a control flow graph, or CFG, represents the possible paths a program can take during execution. The nodes are basic blocks of code and sequences of instructions, and then the edges are the transitions between the blocks based on control flow. Examples of these are if statements, loops, and function calls. So in this diagram, this could be an example of an if statement. It kind of splits off. If it's true, it'll do the one side. If it's false, it'll do the other. And then it comes back together. So you can see all the different edges and paths that this code can take. This matters for PerfFuzz because it maximizes execution of specific edges to reveal complexity hotspots. Instead of maximizing the total runtime, it finds different worst-case behaviors across the program. So every time a branch or loop executes, a CFG edge is taken. PerfFuzz tracks the counts for all these edges simultaneously, and if an input causes one edge to execute more times than any previous input, it is then saved. So why do you think, why might tracking execution counts for each edge reveal performance problems better than just measuring total execution time? Okay, so now going on to the PerfFuzz algorithm itself. As said before, the goal is to maximize the execution count of each edge in the control flow graph. So these are the steps. It'll start with seed inputs, usually just one or two. In the previous example, the quick brown fox jumps over the lazy dog would be the seed input, and it stores those as the parent input. Then it'll select a parent input and generate the mutated children from that input. Then it'll track the execution counts of those children and then save the inputs that maximize execution of some CFG edge. And those will then become the new parent. So this is all repeated until a time limit. Inputs that maximize execution count of at least one CFG edge are favored and have a higher probability of being picked to be mutated. And also, interesting fact, the number of favored inputs at any time is smaller than the number of edges. So could this technique detect memory performance issues, or do you think that you could use this concept to do more with memory? Okay, now we're gonna talk about why they decided to use multi-dimensional feedback. So other fuzzers maximize total execution path length using code coverage, but the problem with this is it gets stuck in the local maxima. PerfFuzz tracks the execution counts for each CFG edge to find multiple performance hotspots, and this avoids the greedy approach. Program performance can be non-convex, and increasing runtime in one place might decrease it elsewhere. So now more details. So these are just some of the key concepts. The performance map tracks the execution counts for each CFG edge, so that's kind of the main component. Then the cumulative maximum map stores the highest execution counts seen so far in the program. And then the new max is when the input exceeds previous execution count for some edge. And then favorite inputs are the inputs maximizing execution for at least one edge, and the selection probability is are the favorite inputs that are chosen more often for mutation. So PerfFuzz is built off of American Fuzzy Loft, or AFL, which I did not realize it was actually a bunny or a rabbit. Did not know that. Very cute. But AFL includes coverage guided fuzzing, mutational input generation, and lightweight instrumentation. So PerfFuzz uses the same mutation operations that AFL uses. So this would include bit flips, random byte insertion, byte deletion or duplication, and then input crossover. It also extends AFL with performance feedback, so PerfFuzz's input selection is also the same heuristics as AFL, and inputs with wider coverage get more mutations. So obviously PerfFuzz tracks execution counts for every CFG edge, and the inputs are saved if they increase maximum execution count for any edge, even if the total path length decreases. So PerfFuzz was evaluated on many different programs, which we're not going to go into, but it was evaluated by execution counts of CFG edges, obviously, the total path lengths, and the ability to expose performance bottlenecks. This was then compared against another fuzzer called slow fuzz and other standard fuzzing approaches. So the goal of slow fuzz is to maximize the total execution path length, not the CFG edges. So this is using the greedy approach and focuses on overall runtime. The limitations of slow fuzz are that it might miss bottlenecks in very specific components. So instead, PerfFuzz obviously maximizes each CFG edge independently. So now back to the word frequency program. If you were to run PerfFuzz on that, these are the three outputs that it would give. So for the first one, it's outputting a single long word. So this one would maximize the compute hash function. Then the second one is a string containing many short words. So this repeats the add word function. And then this last input, this contains many words, and it's also a lot that hash to the same bucket as just the letter T. So this is a lot of repeated traversals of the linked list. So this demonstrates different types of performance stress and how PerfFuzz can see all of these. So performance results was with just word frequency, not with everything else they tested with. And this is also just how long it took, not the other evaluation techniques that they did use later on. But PerfFuzz can execute word frequency about 6,000 times a second, which is then about 20 million executions per hour. And then at the end, it'll output the inputs, causing maximum execution count and the corresponding CFG edge statistic. So that's how we got all those three inputs on the previous slide. So how well do you think PerfFuzz would scale to very large systems rather than this small word frequency program? Now to contributions. The key contributions of PerfFuzz is it is the first fuzzing technique focused on performance bottlenecks, and it then introduced multidimensional feedback. It identifies distinct pathological inputs and it demonstrates effectiveness compared to previous tools used. So some limitations of it include that it assumes that high execution count correlates with poor performance. It misses issues not tied to CFG execution counts, and it requires program instrumentation. Some performance issues could come from things like memory usage or I/O, not just the execution counts. So that's how these limitations come to be. So should fuzzers optimize runtime directly instead of execution counts? I think to be able to answer this question and think about this, you have to compare the different fuzzers that use each different technique. So some possible improvements would be to include direct measurement of runtime cost, to look at memory or cache aware metrics, and also to apply this to large real-world systems. Some practical impacts of PerfFuzz. PerfFuzz could help detect algorithmic complexity, vulnerabilities, prevent performance-based DOS attacks, and just generally improve software reliability. This is, of course, useful for security testing, performance testing, and continuous integration system. Thank you. I highly recommend to read this paper. It was very interesting, and all of their comparisons that they did with slow fuzz and all of the other fuzzing techniques were super interesting, and their graphs were pretty informative. So, thank you.